Welcome. Today's lesson is on total and partial pressures. We've been talking about gases this whole unit, but we've assumed that the gases were just made up of one element or one molecule. We talked about maybe nitrogen or oxygen or ammonia or carbon dioxide. But what if we have a gas that's a mixture of gases, which often happens? Our own atmosphere is a mixture of gases. So let's take a look at this picture. And here we have a box, and we're going to have this represent gases. So I have blue dots represent that there's nitrogen gas, red dots representing oxygen gas, and green dots representing carbon dioxide gas. So if I have a box of all three of these, and I want to talk about pressure, what is the pressure? Well, the pressure is the collisions. So it's the collisions that the nitrogen has, that the oxygen has, and the carbon dioxide has. I can talk about the total pressure of the box, which is the molecules hitting the edges of the box and all the molecules, so nitrogen, oxygen, carbon dioxide. And I can also talk about the individual pressures. How much pressure is due to the nitrogen molecules hitting the box, how much is due to the oxygen, and how much is due to the carbon dioxide. So I can write an equation for this, so don't forget to write it down. So the total pressure, which we symbol as PT, and then T standing here, instead of temperature, this is going to represent total now. So the total pressure equals the pressure of all the individual gases. So for this case, it's the pressure of the nitrogen plus the pressure of the oxygen. And we also call this partial pressure because it's part of the total pressure and the partial pressure of carbon dioxide. So if I knew the partial pressures of each, I could find the total pressure, or if I knew the total pressure and two of the partial pressures, I could find the remaining partial pressure. So what if I know that the partial pressure of nitrogen is 1.53 atmospheres and the partial pressure of oxygen is 2.3 atmospheres and the partial pressure of carbon dioxide is 4.11 atmospheres? All I would have to do is add these up to find the total pressure. So pretty easy. So I'd add these three numbers up and I get 7.94 atmospheres. But I have to remember sig figs, and remember I'm not counting sig figs, I'm looking at the place. This goes to the hundredths place, this goes to the tenths place, this goes to the hundredths place. So I can only go to the tenths place. So the answer here would be 7.9 atmospheres would be the total pressure of this system. So I think that's pretty easy to understand. The total pressure is just the sum of all the partial pressures of all the individual gases in the mixture. So let's try it one more time with a little bit more difficulty. So let's look at this problem. What's the total pressure of a mixture of gases of helium and neon? If I know the partial pressure of helium is 735 millimeters of mercury and the partial pressure due to neon is 1.55 atmospheres. So hopefully you can see that the pressure total is going to be the pressure from the helium and the pressure from the neon. But I can't add these together as they are because one's in millimeters of mercury and one's in atmospheres. So I have to do a conversion first. And you can choose whichever you want to convert unless the problem asks you specifically for one unit. But I usually like to end up in atmospheres, so I'm going to convert the millimeters. So 735 millimeters of mercury times the conversion factor, which is 1 atmosphere for 760.0 millimeters of mercury. And I get a final answer of 0.967 atmospheres. So now I can add the two up together. The partial pressure from the helium is 0.967 atmospheres, plus the partial pressure due to neon is 1.55 atmospheres. And if I add these two numbers together, I get a total of 2.517 atmospheres. But once again, I have to worry about significant figures. This goes to the hundredths place. This goes to the thousandths place. So I can only go to the hundredths place So 2.52 atmospheres is the total. So still a pretty easy problem. What else can I solve using this? Well, I can also solve for the total pressure. I can also solve for the partial pressures if I'm given the total pressure. So write this equation down and let's see where it comes from. So if I want to know the pressure of gas, let's just call it gas A. It's the total pressure times how many particles of A, and that's in moles, are there compared to how many particles total. So partial pressure of A equals the total pressure times the fraction of the number of moles of A compared to the total number of moles. And that will tell me the partial pressure of A. So let's try using this equation to solve a problem. So here's the problem. What are the partial pressures of nitrogen and oxygen if the total pressure is 1.53 atmospheres and you have a mixture of 70% nitrogen and 30% oxygen? So remember, the equation is the pressure the pressure of the individual, such as nitrogen or oxygen. So let's say nitrogen. So the pressure of nitrogen equals the total pressure times the number of moles of nitrogen. That's supposed to be a nitrogen, compared to the total moles. So let's solve for that. So the pressure due to nitrogen equals the total pressure, which happens to be 1.53 atmospheres, times how many moles of nitrogen do I have compared to the total moles? Well, if it's 70%, and I'm talking about percent by particles, 70% means there's 70 particles for every 100 particles. So I have 70 moles of nitrogen for every 100 moles total. And that's what percent means. And so 1.53 times 70 divided by 100 gives me an answer of 1.07 atmospheres. Notice the moles will cancel out. So to find the pressure due to oxygen, I could follow the same procedure, or I could do a simple subtraction. I know the total pressure. I know the pressure due to nitrogen. I can subtract the two, and I can find the pressure due to the oxygen, which would be 0.46 atmospheres. So there you have it, problems with total pressure and partial pressures. So give them a try in your problem book, and thanks for listening.